Okay, this video will be talking about examples for lesson 9, which was continuous probability models except for the normal distribution, which is covered in lesson 10. And we'll also talk about expected value and average value for continuous distributions. Okay, so this first problem says a random variable x is described by the probability density function f of x, which is given by this. Basically, it's kx cubed, but we're only supposed to use it between 0 and 4. The probability is 0 for anything below 0, and the probability is 0 for anything greater than 4. So it asks us to determine the value k that would make this a probability density function, find the probability that k is between 1 and 3, find the probability that x is greater than 3, and then find what the typical value is for the random variable. So go ahead and pause this and then try the problem. Okay, when I'm working on this, I'm thinking, okay, as soon as I see this word probability density function, that tells me this is a continuous distribution, and that means that probabilities are going to be determined using calculus and using integrals. So first of all, for the value k, there's an implication here that this f of x is not already a probability density function. It states that it is, but if it were, it means if I were to take an integral to sum all the values over the range that it's allowed to use, this domain from 0 to 4, it should have a sum of 1 so that it's 100%. So the way I would start this problem is saying, let's find the sum of all the possible values. So this is used from 0 to 4, and they told me that it would be k times x cubed dx. Okay, so let's say at first I don't know what k is, right? So there's some constant there. So one way we could approach this is we could say, let's go ahead and do the integral without the k, x cubed dx, and we could evaluate that. You can either do that by hand, or you could use a calculator's function. I'm going to use a calculator function for that here. So we have a TI-84 here. So I could, for example, use math and then function 9 to do an integral from 0 to 4 variable key cubed dx. So this will give me the area under the curve of x cubed between 0 and 4, and that turns out to be 64. So if the area without the function without the k is 64, then that means because this sum has to equal 1, then this k would have to be 1/64th. Will have to be 1 over 64. In other words, if I were to say that take the integral from 0 to 4 of 1/64th x cubed, that should turn out to be exactly 1. And in fact, I think if I do that, that's exactly what will happen. Let me just go ahead and do another integral to show you that if I took an integral from 0 to 4, and I took the constant 1 over 64 and then multiplied that by x cubed and took the integral of that over the entire range there, that turns out to be 1. So as long as k is 1 over 64, then that means that this is indeed a probability density function. Okay, so the second part says now find the probability that x is between 1 and 3. All right, so for that, what we could say is, all right, I need to use the probability, but this time I'm not going to sum all the way from 0 to 4, which would give me 1. I want just the area under the curve from 1 to 3. And my probability density function I now know is 1 over 64 x cubed. Right? So I would have to do that particular integral in order to find the probability. So let me do that with a calculator. There's various manual ways to do this, but this is not a calculus video. This is a probability video. So 1 divided by 64 times x cubed. This time we'll only sum and find the area under the curve between 1 and 3. And that turns out to be 0.3125. 0.3125. So that would be the probability that this random variable is between 1 and 3. If I wanted to find the probability that x is greater than 3, right, similar, we're going to take the integral. This time, let's see, greater than 3 means we'll start at 3, and we'll integrate up to the max value that we can have, which would be 4. We're not allowed to use this beyond 4. So it's just going to be the integral of the probability density function, but from 3 to 4. Okay, and so again, I'll do that with a calculator here. So integral from 3 to 4 of 1 over 64 times x cubed. And that turns out to be 0.6835. Right? Okay, so actually finding probabilities for continuous probability density functions or for continuous cases is some of the easiest probability problems of all. Even though it involves calculus, it's just the computation of a simple integral. As long as we have a probability density function, we may have to adjust the constants so that it turns out that when you sum over the entire range there, it turns out to be a 1. Okay, so this last part says, what is the typical value for this random variable? Okay, so typical value. Well, there's two expressions that we can use for typical value, right? One of them is called the expected value. Expected value, that is, we have to take the integral, and the values of the variable are x's, and the f of x is a probability density function. It's really the continuous variable analog to taking a sum of data values times their probabilities, right? But the data values are x's, and the f of x is a probability density function, right? The other thing we can do is find the average value, which means we sum over the entire region the f of x, and then we divide by how wide the interval is, right? So how do I know which one I need? Well, that depends on what f of x is. If f of x is a probability density function, then that means we need to use the expected value because f of x isn't the value, it's the probabilities associated with the x values. If instead f of x is a value itself and not a probability density function, then we use average value, right? But in this case, we don't have that, right? Our f of x represents a PDF, so we're going to use this version. The expected value, therefore, is, and we have to use the entire range, so it'll be from 0 to 4. We take a sum of all the values times their probabilities, right? So in this case, that would be integral from 0 to 4 of x times 1 over 64 x cubed, which is really 1 over 64 x to the 4th. So again, I'll use a calculator to do the integral, and this will be from 0 to 4. I'm just going to enter that as 1 over 64 and then times x to the 4th, combining the two x terms there. And then that would be 3.2. So what we could say is that if we have this probability density function that's gives values of probability where the values can be between 0 and 4, then because of the shape of this, the most likely value, the typical value, the expected value, would be 3.2. Okay, let's take a look at another probability problem. It says a food bundle is dropped into an enclosure containing a gorilla, and by the time the gorilla begins eating, and the time until the gorilla begins eating the food is recorded in minutes. This experiment is repeated many times, and the times are found to be modeled well by an exponential model with lambda equals 1.4. What is the probability that the gorilla will wait at least 2 minutes before beginning to eat? So pause the video and then try this problem. Okay, so in this case, we're told to use an exponential model, which is another continuous probability model. In this case, the probability density function is given by a standard formula. F of x would be equal to lambda e to the negative lambda h. That's a standard model for continuous probabilities. And so in this case, since they told me lambda is 1.4, it would be 1.4 e to the negative 1.4x. That's our probability density function that's given. Right? So if you look at what that would look like, if I looked at different values and their probabilities, the PDF versus x, it's an exponential with a negative here. It's an exponential decay, right? This is the probability model, right? So starting at 0, we won't get all the way to 0, and we could go to potentially infinite amount of time for the gorilla to wait until he begins to eat the banana, or she begins to eat the banana, right? But what we're trying to find is the probability that we have to wait at least 2 minutes. So right here is a boundary at 2 minutes, and we're trying to find the probability to the right of that, right? So rather than doing some kind of an improper integral where we take the integral under this curve from 2 to infinity, what we're going to do is recognize that this plus this has to add up to a total of 1. So I'm going to write it this way. The probability that we wait at least greater than 2 minutes, that's equal to 1 minus the probability that we wait less than 2 minutes. Okay, and for this probability that we wait less than 2 minutes, we're just going to integrate from 0 to 2 the probability density function of 1.4 e to the negative 1.4x. And again, we could do that in a calculator. If we wanted to do that, we could say the left-hand probability there is the integral from, let's see, math 9 here. We could do from 0 to 2 with 1.4, and then we'll use e to the x and negative 1.4 times the variable key, and then dx. So this is going to be the probability that the gorilla eats in less than 2 minutes, 0.9392 approximately. Right? So this would be 1 minus 0.9392, and therefore the probability on the right-hand side is what's left, so 0.0608. So basically about a 6% chance that the gorilla waits at least 2 minutes before beginning to eat. Another continuous probability problem where they essentially gave us the probability density function. Okay, let's take a look at the next problem. So the next problem says, in the old days, before digital video recorders with time-shifting capabilities, if you wanted to record a show to watch later, you used a video cassette recorder, a VCR. And you had to wait until the show finished recording to the end before watching because it was still recording, and those devices you couldn't play back and record at the same time. So if you happen to come home, let's say suppose you set your VCR to record your favorite show because you knew you had an appointment, you wouldn't be home before your show started at 7 o'clock, then, and maybe the earliest that you could be home would be 7:15, and it's actually likely, equally likely, that you'll arrive at home anytime between, say, 7:15 and 9. Then we could maybe ask this question: what's the probability that you'll have to wait more than 30 minutes for the VCR to finish recording before you can start watching your show? And B, what's the average amount of time you should expect to wait to watch your show once you arrive at home? So pause this and then give it a try. All right, so this is also a continuous probability problem. We could wait any number of minutes. And the issue here is it says we're equally likely to arrive home at any time between 9:15 and, or 7:15 and 9, okay? So what we could do is say, okay, that means this is what we call a uniform probability density function, right? So let's kind of mark this out. 7:15 p.m. and 9 p.m., we are equally likely to arrive anywhere in there, right? And so what would be if we arrived, if the show's going to end at 9, and let's say we arrived right at 7:15, then that's a total of, well, let's see, 9 to 8 is 60 minutes, right? And then from 8 back to 15 minutes is another 45 minutes. So that's a total of 105 minutes. So the maximum amount of time we could wait would be 105 minutes. That's the max time that we could wait. The minimum amount of time we could wait would be if the show's going to end at 9, right? And we could potentially arrive home right at 9. Is that what it said? The show is going to end at 9. Yeah, okay. Then we could potentially wait 0 minutes if we walked in the door right at 9 p.m. when the show was done recording. Does this show tell me that? Yeah. Started at 7, earliest is that, equally likely. So the implication here is this is a 2-hour show. Let's make the assumption that the show ends. I think the problem should have stated that. The show ends at 9 p.m. We're going to make the assumption that that's true. Okay, so the minimum amount of time we could wait would be 0 minutes if we walk in the door literally as the VCR is shutting off. All right, so if I were to try to graph the probability density function here, right, then the smallest amount of time we could wait, this is going to be wait time here for our variable. Let's call that x, the wait time. We could wait 0 minutes, and the maximum would be 105 minutes. And the probability is equally likely to occur at anywhere in that time. There's no particular one time that's more likely than other. So the probability density function would be uniform. Okay, so one thing we know about the probability density function is that the area under the curve for the entire domain that it's allowed to be used has to sum to 1. So if this is a rectangle, and we know that this length right here is 105, then hopefully you'll agree that this width here would have to be 1 over 105, so that if I multiply length times width, I get an area of 5. And what that means is that the PDF function is a constant. It's just the constant 1 over 105. The probability is always 1/105th. Okay, so now we're ready to actually figure out the question. In part A, it says, what's the probability that you'll have to wait more than 30 minutes? So 30 minutes here, and we want this area under the curve, right? So for part A, we're finding the probability that x is greater than 30, and that would be the integral of our probability density function of 1 over 105, but integrated from 30 up to the max value of 105. And we could do that in a calculator. I use the integral features from 30 minutes out to 105, given that the probability density function is 1 divided by 105. No variable key here. It's not varying depending on the x. That would be 0.7143. So 0.7143 is the probability. Okay? So about a 71% chance you're going to have to wait 30 minutes or longer when you come home. Okay, and then the last part of the question says, what is the average amount of time you should expect to wait to watch your show once you arrive at home? So that is either going to be an average value or an expected value. And like we said in the last problem, that depends on what f of x is. If f of x is a probability density function, then that's not the value. That means that we have to use the expected value. That means it's going to be the sum of data values times their probabilities. Right? So in this case, it would be an extra x times the probability density function of 1 over 105. And because we're looking at all the possible values, this would be from 0 minutes to 105. All right, so if I plug that in a calculator, and we'll use integral features again from 0 to 105, if we have the x times the probability density function 1 over 105 dx, that turns out to be 52.5 minutes. Okay, so what they're saying is, on average, given this scenario, we should expect to wait about 53 minutes typically for the show to finish. Now, of course, we probably won't wait exactly that amount of time. We'll wait, any amount of time between 0 and 105 minutes, but it'll typically be around 52.5 minutes. That's the average amount of time we would wait. Okay, let's take a look at another problem here. So 9.4 says the high temperature of a certain city is given by the function t as a function of d, 75 minus cosine pi d over 182, where t is the high temperature in degrees Fahrenheit and d is the number of days after January 1st. What is the average high temperature for this city? Okay, so this is some kind of a sinusoidal here. I think it just says, what's the average high temperature? Okay, so again, average is a word that means typical, right? And there are two choices. There's the expected value and there's average value, right? Expected value is the one where the f of x is the PDF value, and we have to have x for the values, and the average value is where we sum up all the f of x's and divide by the width, b over a, okay? So it depends on what f of x is, and in this case, right, the f of x, this temperature, that's actually the value of the temperature. That's not a probability, that's the value of the temperature itself. So we're going to need to use the average value formula here. So let me write it again. The average value is, in general, from a to b, where that's the entire interval you can use it for, the entire f of x without the extra x divided by b minus a. So here we would be talking about average high temperature for the city, right? Presumably we're talking about for the entire year. So that would be from day 0 to day 365. That function, 75 minus cosine pi, and then I'll put the variable key in here, x, over 182, dx, right? And then we'll divide all that by 365 minus 0, the width. It's kind of like dividing by the number of elements there. So let's go ahead and do that in a calculator. We're talking about trig here, and unless we explicitly know that we should be in degrees, we should generally, for calculus problems, be in radians. Okay, so I'm going to go math 9. We're talking about from 0 to 365 days. And the probability density function is 75 minus the cosine of pi times the variable key divided by 182. Okay, close the parentheses for that. Okay, and then x. So this is the numerator of the fraction. And then I'm going to divide that by 365. 365, that gives me 77.997, or about 75 degrees. 74 point something, right? Was that what that was? Let me check again. Yeah, 74.99, so 75 degrees. Okay, so the average temperature in this city over all the days is 75.0 degrees. And we used average there because the f of x wasn't a PDF. It was the value of the function of it was the function for the value that we were trying to find. Okay, last problem. It says in American football, a field goal is made when a kicker kicks the ball between the uprights of the goalposts. The goalposts are 18.5 feet apart and are located at the back of the end zone, 30 feet behind the goal line. Football kickers are quite accurate. Assume that the probability of getting a kick going in the direction intended follows a cosine function, where it's cosine of 2 theta, where theta represents the angular error from the intended kicking direction. Okay, A, if a kicker is kicking from directly in front of the goal on the 10-yard line, what's the probability of a successful field goal? And then B, if a kicker is kicking from directly in front of the goal line on the 40-yard line, what's the probability of a successful field goal? And then considering only positive angles, what is the typical angular error of a kick? Okay, challenging problem here. So pause, think about it, give it a try, and then unpause. Okay, well, let's give this a try. First of all, I think we're going to have to figure out what the probability density function is, because we're given a function, right? But I'm not sure that it's actually a PDF yet. So this function, f of x equals cosine of 2 theta. I'm going to use theta for the angular error, like it said. What would that actually look like? Well, if you plot that, actually, let's try that. Let's do that. Let's take some values here. I'm going to go to y equals, and I'm going to put cosine of 2 times the key there. We're still well, actually, we're in radian modes. This one said this is intended kicking direction, right? So I guess we could decide, should we do degrees or should we do radians? So I'm going to break out of the pattern here. Let's do actually degrees for this, because I think it's easier for physical problems to think in terms of degrees. So I'm going to go to degrees here for the problem. And let's just do a quick graph. I'm going to set the window to go from like negative 90 to 90 degrees, and negative 90 degrees to positive 90 degrees, and we'll see what that looks like. Okay, so let me just do a graph here. Okay, so definitely there's a sinusoid here, and it looks like it's crossing 0 here. And I guess we could figure out exactly where that is, algebraically. But let's find it. Let's find it just graphically here. I'm going to move the window. I'm going to make this a little smaller, maybe -1 to +2 or something like that, so we can see that a little bit better. So here's that thing they said that we should use as a probability density function. If I put a trace on here, actually let's do second trace, and I'm going to find a 0. We're at 0. And let's do this. We'll go down here to the left side to be the left bound. Everything looks symmetrical here. So that's to the left of a 0. That's to the right of a 0. That's the guess. Looks like 45 degrees. So just kind of labeling this, it looks like basically there's other things going on, but the probability density function makes sense if we use it from -45 degrees to +45 degrees. And it has what looks kind of like a cosine, part of a cosine function there. Okay. So if I want to test to see, is it a PDF? Is this a PDF? Then I can go ahead and just take an integral from -45 degrees to +45 degrees of cosine 2 theta. d theta, and we'll see whether or not that does in fact sum to 1, which it should if it's a probability density function. If not, then that's okay. We can fix it by just making a multiplying by a constant. So let's do math 9 here. Actually, let me get out of there, and then we'll do math 9. So we're going to go from negative 45 degrees to positive 45 degrees, and then we'll put cosine 2 times the variable key. Wait, I need to close the parentheses here, and then x. Okay. So that turns out to be 57.29, right? So since this is like 57.29, then that means the real PDF is 1 over 57.29 times the cosine of 2 theta. So I needed to do that first so I can make sure that I'm dealing with an actual probability density function, and I am here. Actually, let's just round it to 57.3. So this will be 0.3 here. I'll change that. 0.3. Okay, 57.3. Okay, now we know we have that. And it says if the kick is being kicked from directly in front of the goal line on the 10-yard line, what's the probability of a successful field goal, which means it goes through the uprights. So let's try to draw a picture of the situation. Right? Here's the goal line. Right? We're on the 10-yard line, which is maybe here. 10-yard line, and it says that the goal posts are 30 feet behind the goal line. So this is where the posts are, right? And this is 30 feet, which would be the same as 10 yards. So 10 yards behind the goal line is the posts, and 10 yards in front of the goal line on the 10-yard line is where we are kicking from, right here. So where is the goal post? Well, let's put the goal post right here, okay? And we're kicking from right here. All right, it says directly in front of the goal. Okay, so we're trying to figure out what the probability is that we would make it in the we would make it in there. So this width they said was 18.5 feet, right? Let me switch everything to feet. I think here we're gonna go with feet. There's 30 feet here, and this is 10 yards, which is also 30 feet. Because ultimately, I have to figure out where we are in this probability density function in terms of an angle, right? This probability density function is expressed in terms of angles. So I need to find the angles where we're going to be, right? All right, so let's do like a right triangle from here over to the edge of the goalpost in here so I can figure out this angle in here. That's the angle of error that I can have and still make the goal. Okay, so if this is, let's see, a total of 30 and 30, which would be 60 feet, and then this width would be half of the 18.5, so that makes a triangle. Let me draw it over here. Let me draw it over here. So that makes a triangle where this is 9.25, and this would be 60 feet this way. This is a right angle, and I have this angle. Well, for this angle, this 9.5 is the opposite side, and this is the adjacent side. So I could say the tangent of this angle theta is the opposite side over the adjacent side. And therefore, I could solve for this by taking the inverse tangent of 9.25 over 60. So let's do that. If I take the inverse tangent of 9.25 over 60, then that means we're at 8.764 degrees, 8.76 degrees. Let's just round to that. Okay, and that means that we're going to make this goal if we are anywhere from negative 8.76 degrees to positive 8.76 degrees. If we're in that region, then that means that we've made the field goal. Okay, so what I'm really saying is here's this PDF, right? It has the shape of a cosine wave, and I want to know what is the probability of being in the region from negative 8.76 to positive 8.76 degrees. All right, so for that we would use an integral. We would say, all right, the probability is going to be from negative 8.76 degrees to positive 8.76 degrees. We're going to use the probability density function, which is 1 over 57.3 times the cosine of 2 theta d theta. And then we'll use a calculator to find that probability. All right, so if I do math 9, I say negative 8.76 degrees for the lower limit of integration, 8.76 degrees positive for the upper limit, and then I use 1 divided by 57.3 times the cosine of 2 times the variable key, close parentheses, dx. That should give me the probability of making the field goal from the 10-yard line. So if this really is the PDF, the probability would be 0.3012. 0.3012. So about a 30% chance for this kicker if this is representative of their accuracy. Okay, for part B, it says the kicker is it's exactly the same except that the distance has increased to the 40-yard line. So I think all the geometry is the same, except that I'm kind of running out of space here. Let me see if I can move this up a little bit. And then we'll continue. The only thing is we're going to try to change the geometry. We're on the 40-yard line now. So that means that the triangle would look like this. There's still 9.25 feet from the middle of the goalpost out. But this time I would have my 30 feet, and then instead of 30 feet, right, it said 40-yard line, right? So 40 yards, right, 40 times 3, that would be 120 yards. So it'd be 120 yards plus the 30 yards back to the goalpost. So this would actually be 150 feet. So if I'm 40 yards in front of the goalpost, or front of the goal line, that's going to be 120 feet plus the 30 feet, the 10 yards to go back behind the goal line to the post. Okay, so this angle will now be, the second angle is the inverse tangent of the 9.25 divided by, this time 150 feet. So that angle, if we do that in the calculator, if I do inverse tangent of, let's see, we said 9.25 divided by 150, right, 150, that turns out to be 3.5, let's round it to 3.53 degrees. 3.53 degrees. And so that means the probability, right, of that occurring would be integral from negative 3.53 degrees to positive 3.53 degrees of that same PDF. 1 over 57.3 cosine 2 theta d theta. And if we did that in the calculator, math 9, from negative 3.53, right, 3.53 to positive 3.53 with 1 divided by 57.3 times the cosine of 2 times the variable key, close parentheses, dx. The probability decreases to only 12.29%, right? So the probability would be 12.29. Okay. So a 30% chance of making the field goal from the 10-yard line and a 12% chance of making it from the 40-yard line. Okay, and the last part, it says considering only positive angles, what is the typical angular error of a kick? So typical value is either going to be, again, an expected value or an average value. So for average value, the f of x would have to represent the value. And for expected value, the f of x represents a PDF. And since we have a PDF type here, that means that for part C, we're going to find the expected value. And it said for only positive angles, considering only positive angles. So I'm going to go from 0 to 45 because that represents all of the positive angles, right? In the PDF here, right, from here all the way out to the maximum angle, that's from 0 to 45. Right, we'll have the extra x times the probability density function, 1 over 57.3 times the cosine of 2 theta d theta. Okay, and if you plug that in a calculator, it just turns out to be 8.2. And so that means typically this kicker is off axis by, on average, 8.2 degrees. Okay, very tricky problem, the trigonometry behind that, but just another use for continuous probability density function. Okay, that wraps up this video. and yeah, move on to other videos. We didn't talk about the normal distribution because we dedicated all of lesson 10 to that. That's another continuous probability density function, but it's so commonly used and we use it in so many different ways, we dedicated a whole lesson just to that.